Welcome to Made Up of Wires. Sometimes I play games, but usually, lately, I'm decompiling Symphony of the Night. So what does this mean? There's a project that I found just a couple months ago. These guys have been working on this for a couple years before I got here. To recreate the source code for Castlevania Symphony of the Night, possibly the greatest Metroidvania game ever made. Castlevania Symphony of the Night was originally released for the PlayStation 1 console in 1995. It's been ported to just about everything. There was a joke recently in the Discord about how it's possibly one of the most ported games after Doom, and will be running on thermometers before we know it. Many of the ports use much or most of the source code from the original PlayStation 1 game, with a few tweaks and variations for integrating with how saves work, achievements, translations, and different things like that. For the most part, these games aren't running under emulation. They're actually recompiled and retargeted for each of the platforms. What's funny is things like the the PSP version actually have the original binaries from a PlayStation version of the game, not necessarily exactly the same as the PlayStation version that we had, but it doesn't use those. Okay, so in this stream, we are going to take a function that hasn't been decompiled, that we don't have the source code for, look at the assembly that came from the original game, and turn that back into C source code. Sometimes that's easier than not. We're focusing on weapons lately, so most of these functions are relatively small and can go relatively quick. I hope in about an hour or so to go from source and kind of walk through what it means to decompile. If you go to SOTN.z.dev, you can see what the progress is so far. So there's one function left in the main game engine that hasn't been decompiled yet. It's a little tricky one. I think I said last stream, I have a function that's a 99% match. There's one section that I can't get an exact match on, and I haven't looked at it since the last stream. But it's one of those things where sometimes you walk away and come back later and the error is obvious. There are a bunch of programs or binary objects that have been fully decompiled. The Richter program, we're going to be working on the first weapon object or module library overlay today. Several stages have complete code. So far, we've not attempted to decompile everything, but just kind of a small piece of the various types of overlays that exist. So in the PlayStation development, you have a main program that largely consists of the SDK and library functions. That loads into memory a main program. In this case, our main program is dra.bin, dracula.bin, and it will load that into a specific address and then call a function within that memory address. In turn, that function will load other modules, and it can specify its own ranges of memory addresses for where those get loaded, but usually it's reasonably consistent. So each level, for example, starts at the same memory offset, usually starts with some type of header that defines functions for the main program to call into that level or stage. And that's, for the most part, how it works. So we have a bunch of memory addresses that are extracted from the object files as they exist. And then what we're doing is taking the code in those object files and trying to convert that back to C. So how does this work? So one of the tools that we're going to be using is called decomp.me. It is a social decompiling tool. That's something 15 years ago that would have been somewhat funny to talk about. We're also going to be using Splat, which is a tool that was originally written for N64 decompilation. And that takes the objects or files that were originally on the PlayStation disk, splits them up into parts, finds function entry points in the code for those functions, as well as assets and other things, and just helps us understand the structure of those files. So going over to a terminal, first we're going to find a function. And so a lot of times what I like to do, and especially for streams, is find a relatively small function that I think we're going to have success in decompiling. A lot of these can be long, they can be complicated. In my free time, I'm working on the sprintf function, which is POSIX style string formatting function that has a lot of complexity to it. Something that'll take many, probably dozens of hours to decompile. This we're going to try to do something in the next hour or so. So assembly files are extracted to an ASM directory. So I'm going to look in ASM. We're using the US version of the game, so ASM US. Make this bigger and readable. We're looking at the weapon module. Functions that have not been decompiled yet go into a directory called non-matching. We're going to look for files that end in .s, and we're going to get a directory listing of those. So here's a bunch of files. They're assembly files. I'm going to use awk to get the size and the name of the file. And I'm going to sort them by their size in reverse order. So we have a bunch of assembly files based on their size. Yesterday we did a weapon 15 file. This is a weapon 16 version based on the size, and what I remember from yesterday, I'm guessing that's very similar and probably something we could do, but it's a little too similar. I like to move on to something different. So let's look at this weapon 7. I'm not sure what weapon 7 is, but this is the assembly, and we'll look at, there's a corresponding C source code file that goes along with it. So this is the shield rod. That's fun. So everybody knows what the shield rod is. It's a weapon that adds a damage component to a shield. And the function we were looking at is this func pointer 80170008, and we can see in the C file that this is being included as an assembly file because we don't have the code for it yet. So our goal today is to replace this line for including that assembly file with the C code that would be compiled back into the same assembly. So to do that, we're going to use decomp.me. So off screen, I'm going to copy this file. back to decomp.me, start a new decompilation. This is already preset to what I've been working on, so we're looking at MIPS assembly for the PlayStation. We have the Symphony of the Night preset, and we're going to paste our assembly code in here and create a scratch. This will create a new workspace. Decomp.me will attempt to decompile the code based on a context that we've given it. A context is kind of like a shared header file, and it'll try to get as close as it can to something that looks like the generated assembly, the assembly that we had before. So we have the decompiled version on the left. On the right, we have a target column. This is the assembly that we're trying to match. Another column with what our C code currently compiles to, and then any warnings or problems, compiler output. So when setting up a new scratch, one of the first things I do for this project, the PlayStation SDK provides definitions for string compare, copy, length, and memcopy. We don't want to use the ones that are built into GCC, so we add the no built-in option. This is actually a relatively short function. Hopefully we can do this relatively fast. We have one function declaration that it found for us. I like to move these into context, mostly to keep the workspace clean. And so as is, without touching any code yet, I'll get rid of some of this superfluous comments, we have a 55% match. So the goal is to get as close to 100 as possible, get this number, this 5003 number, get that down to 0. We won't be able to get there completely due to some addressing issues that I could talk about as we change those. But this is relatively good starting point. Functions that act, so an entity in Symphony of the Night is any object that has some behavior associated with it. It doesn't necessarily have to draw to the screen. It just has to have a lifespan. So it could be an enemy, it could be a weapon, it could be Alucard. It could be, some Orlock's spit, for example. And so a lot of functions, the first argument that they take is an entity, and we treat those almost like what would be class methods if this were an object-oriented program. And so the convention, instead of taking arg0 as the name to make it look and feel more like an object-oriented language, we use the word self for functions that look like class methods. So all I've done is replaced arg0 with self, and that won't change this compilation value at all, but it'll make things easier to read. A lot of this is going through trying to figure out what variables that the decompiler doesn't know what they're for, determining what they're for, and then giving them names that make it easy for humans to understand. The next thing I like to do when I start out is look for common idioms that the decompiler can't detect, or that the assembly extractor can't know about. So for example, there is a API structure that has pointers to functions that we have symbols for that go directly into that structure, but that's not how those are accessed in code. And in this case, it's not going to make a difference. But these functions are usually accessed through struct members, struct fields. So we're going to change that. That's actually going to lower the matching code, because we have now over here, it was thinking I want to go to this symbol called GAPI alloc primitives, but we're changing it to some offset in the GAPI struct. When that compiles down to machine code, those are going to be exactly the same. The decompiler can't know that, but we know that. Looking at our side-by-side comparison, we have different symbols in this column. It tells us what the difference is between the two. So I is for immediate value. So here we're pushing 32 bytes, pushing the stack pointer out by 32 bytes. In ours, we're doing less than that. So something is requiring less space on the stack in ours than it is in the compiled version. Usually we don't have to worry about that directly. We'll figure it out as we go along. R means that a register is different. So in our version, the register S0 is being used. In the original, the register S1 is being used. We don't control directly what registers are used by variables. The compiler has to choose which it's going to use and for what reason. When we get the code structured the same as what the original was likely structured as, those registers will fix themselves. So usually it's not something that we have to worry about. It just tells us that somehow we're using the wrong types, we're using the wrong ordering of loads or stores, and so we need to fix that. Let's see. When there's an arrow like this, that means there's code that's being generated in the original that we don't have. And the line here is your instructions are wrong, everything's wrong. Figure out what's wrong. And we'll get to that, we'll figure that out. There's a few things in here that we'll clean those up without having to worry about them directly. A lot of times, decompiling the functions is more about understanding the idioms that are used in the code base and repeated over and over and over that the team likely was doing, and just repeating those in the project rather than understanding the assembly directly. Understanding the assembly is valuable because you want to know what an add or a store or a branch or a comparison, what those instructions look like and what the C code would look like to go along with them. But once you've decompiled enough, that's not where you're spending your time. Okay, so let's get into the decompilation. And so first, after setting up the project, after getting my function there, I like to go through and replace variables with common idioms or try to get rid of variables directly. So the first one we start with, this is written, it's not quite KNRC, but it's an older style of C where variable declarations come first in the function before any code is executed. So we'll always see those at the top of the function. We have a primitive pointer. It is getting the value of this allocate primitives method, and this is going to this is typically called prim. That's the convention that's used. So we're going to just replace temp A0 and give it the name prim for primitive, just to make this easier to read and make it more consistent with the other code. Oh, is it? Yes. Temp V0. Sorry, I misspoke when I said that was the return value of allocate primitives. Temp V0, sorry, is the return value there. That is going to be an index into a set of primitives, and we are going to call that prim index, which is another convention. So we have our index and we have our primitive. Now we're going to go through and look for places where variables might be being used superfluously. So in this case, we store the primitive index in a variable, immediately assign that to something in our entity that we're operating on, and then don't really use that again. So this actually, all this can be inlined, and then we can use the self version here. And the compiler's smart enough to know that it can store that off. And that gave us, so going back here, so anytime you make a change, you want to see how is this affecting the code. We start at 5013 differences, and we're going to do that, and we end at 5013. So it didn't actually change anything, but it cleans things up and removes a few lines, less to think about. Okay, so one of the things that an optimizing compiler will do is find segments of duplicated code and then try to repeat those, try to reuse those to reduce code size. Sometimes it's valuable, sometimes it's not. In this case, the compiler generated code where there's a jump when we don't have the a valid index value. We're going to jump down and go to this destroy entity and then return. This is common. That's not actually what the code was originally written as. It was written as this, and that gets us back to the same thing. But more likely it was actually written like this. When the prime index is, or the primitive index is 1, destroy and return. Otherwise, do this other code. And in this case, no difference. So the code can be in a significant number of different shapes and generate the same assembly, which is worth noting. All right, so what can we do next? One of the common things that the decompiler likes to do is take this priority, we can see the line that's generated here, and put it in the wrong order. So we'll move that above draw mode, and that actually gave us quite a bit of additional match. So we'll save that. Could you tell that from looking at the original code that would have provided such a benefit? Probably not. But when you've gone through enough times, that becomes a relatively common thing. So one of the other things is it likes to cast, add a lot of casts that are unnecessary. So we're going to get rid of these casts. Sometimes it helps, sometimes it doesn't. In this case, no difference. Finally, we'll take things like a plus equals 1 and change it to a plus plus. In this case, that doesn't help. Sometimes it helps tremendously. All right, so nothing else is standing out super obviously to me, so I'm going to go through and just clean things up to make it a little more readable. And along the way, see if there's anything that stands out. Sometimes we see this, it doesn't equal 0, we can get rid of that check because that's anything that doesn't equal 0 is a true statement in C. Okay, we'll save this. So we have a few areas around line 13 where the code we have is very different from what is being generated. Sometimes I'll go back through and there may be things that are lost in translation. Go back through and just check to see if possibly something was missed along the way. I don't see anything super obvious. So let's see what we're trying to do here. This is one of those rare instances actually where we do have to go through and start looking at the assembly and see what might be happening. All right, so we're looking at the setting this position. We have a call to random. This is interesting that it's doing a divide that would appear to do nothing. One thing that is not obvious to me why the compiler didn't do this. But so velocity is set. However, the position isn't immediately affected by that velocity. So sometimes I like to put some code in just to see what may have changed. Anything there. There is actually a multiply instruction here that I'm not familiar with, and we're gonna have to figure out what that's for. Just because a function is small doesn't necessarily mean that it's easy to decompile. I'm going to go back to the project and see if there's a function signature for this particular function. There is. I'm going to make sure that we have the correct signature for it in our project, or our scratch here. And we don't. But that doesn't change anything. And then double check this other one. Oh, that's the same function. Okay. The next thing I'm going to do is look for existing examples where the entity position is being set. And see if any of those So this, let's take a look at this weapon 15. Okay, I was wrong about those original instructions. So it's move from high and move to low. What would we be doing? Okay, so let's talk through what's happening here. So JAL is an instruction to jump to a function, so in this case rand, to generate a random value. We're then taking the modulus of that return value by 16. So one possibility here is that all this was being done within the context of a 32-bit integer, but we are trying to go and put this into a 16-bit integer. So some of the operations may be slightly different. So let's try to pull those out and see if that works. So we'll call this delta x. I'll say delta x does these things. And then we're going to add delta x. And does that, so that gets us a little closer. Let's look at this line. Still not perfect, though. Instead of doing a oh, this is interesting. Okay, so this is saying if delta x is less than 0, that's not quite right, but it's getting a little closer. We're doing this divide, which is weird. And this same minus 8 photographs was actually divided by 8. Or divided by 16. Let's look up the So we're, okay. I think I figured it out. So we're doing 16 divided by rand. And I don't think this, I was thrown off by the break branch, which is a, let's check for 0. All right, that gets relatively close. So instead of a mod, it was a division. Let's see if we can get rid of what's odd. Let's see if we can get rid of this. So let's take this and shift it. I'm not sure where the I'm trying to match that the move high and the move low. We're not getting either of those. So this is the same as OS1. If we take all that and we'll shift it by so this is where we're grabbing we're doing 32-bit operation, but then we're grabbing the high bits. So we want to do this and then mask. Let's cast this. It's getting us closer, but still not quite right. Actually not as close as it was earlier. Well, let's do this. What if we just, I don't know, we knew that's division. So let's look for that in the existing code. See if anybody has run into this before. So we're going to look for division by rand. What about any type of division? So it seems like there's something else going on here. We'll come back to it. This gets us a little closer though, and we'll do the same thing on this other one, and we can get rid of a bunch of this for now. But so this is going to be, it looks like the same thing. Okay, so that's getting much closer. Still not quite right. We're still loading the low side of that versus the high side. But as I said kind of at the beginning, as you get closer, the stack is going to work itself out. And so we see at the top, we no longer have a difference in stack. We don't see a difference until we get to these functions down here, which are acting a little funny. One thing I'm going to try, so there's a macro that we have to take fixed values. So unlike modern computers where math with decimal points is often done with floating point numbers. The PlayStation didn't work on floating point, it worked on fixed point. So we'll have 16-bit values, for example, that are 32-bit values that have 16 bits in the numerator, 16 bits in the denominator. I'm sorry, not numerator, numerator and denominator. Yes, sorry, that is correct. Floating point works on some some number of bits that are used for precision, and then some number of bits that are used to multiply by a power of 2 to move the scale of that value. And so in the PlayStation, the scale is fixed, and we're just using numerator and denominator to I just want to make sure that, so we have this here and our 10 there. So when we moved it to a fixed, all those stay the same, yes. And here is the same. So let's see if we have that in. So looking for lines with the fixed macro. Also use rand. And so what if we change this to val? And what if we change this to a multiply by? So one thing I notice immediately is that we're treating this as unsigned. But the generated assembly is treated as signed. Sometimes what is convenient to do is pull the statements out into separate lines, because then you get more details about where particular things are happening. But the compiler doesn't seem to be generating anything I can't spell. Okay, so here is where we're loading our let's move these back. So I'm primarily trying to just permute this in different ways and see what the results are in the assembly. None of this is making much of a difference. And this is the time in the show where I introduce the permuter. So we know that this particular, we have some slight differences in our implementation here. That got us much, much closer. Some slight differences in our implementation that actually gave us the high short. This is wrong. That got us closer. So slowly, slowly we're inching our way. It's not clear to me though why are we loading? So let's try this. Why are we loading a unsigned version of this value? So let's take I'll say that this is velocity x, and velocity x is fixed value. Still That's closer. So now we're just registers away. So here, we're going to subtract the 8, but we're going to do it next. Subtracting by 8. And it's not the same as shifting by 3. So we're one instruction away. What else does subtracting 8 from divide by? Okay, so we have everything but the divide by, or the subtract by 8. Our registers are also still screwed up. Okay, well, we're getting close. So let's look at the rest of this. Line 18. Okay, so we're missing a store. At offset 6 of this, we're supposed to be storing a value, but we're not. Or no, we are storing a value, but we shouldn't be, and that's happening on line 16. Oh, here, of course. So let's try this. I don't think that's the case, but I'm going to try, store word, load high upper. These operations are happening out of order. Why? I'm not sure. Let's try moving this below. That doesn't work. Let's save where we are and assess. So So just a few things off. It's relatively common for instructions like this to be pulled out of order because sometimes memory operations take longer than expected. I don't think that's the case here, though. So I've hinted at it, but let's bring out the permuter and see if that can do anything. So if we make this project in the terminal, what we should see is that all of the objects that we've created so far are matching. So all the code that we have that's compiled into C, along with all the assembly that hasn't been decompiled yet, is creating objects that match what were on the original PlayStation 1 disk. We're going to copy our function that we've been working on over. We know that it doesn't match, and it's going to have about 300 differences. And that's okay. And when so we're going to make this project. Oh, that's interesting. So the function signature is slightly different. Change that to match. What? Because I was decompiling the wrong function. No, I'm not decompiling the wrong function. I'm looking at the wrong file. That was a close one. Sometimes things can get confusing, especially when you're deep in thought. So let's try this again. We're going to take our function and paste it in place of this include a assembly, make, and it fails, of course. We can see that, yes, there's a bunch of differences between ours and theirs. Sad. But we're going to use a tool that somebody's written called the Decomp permuter, which will look at that function of ours and try to figure out what is going wrong. So we're going to take our C file, we're going to take the function that we're trying to match, already it's found some changes that we can make. Oops. Let me put the correct window up. Okay, so here's our window. So we're going to take our C file, which is weapon 07. We're going to take our assembly file and let the permuter try lots of different variations of the code and see if it can find something that would solve our issue. While this is running, this will run through, so we might be able to do a few dozen permutations per minute while trying to finesse this into something that's going to work. But the permuter, and it's not doing it intelligently, but it's already tried 2,500 of these, and so we can see what what it's found. So it outputs into different directories and will give us a diff of what it found. So this thinks, for example, that if we pull a primitive out before we use it, that will get us closer. And it does, quite a bit closer. And that cleared up most, oops, wrong window. Let's try it again. Okay. So down here, it thinks that if we pull out this, instead of inlining this into the function signature, why is this doing this? If we pull this out into its own variable, we can reuse the primitive variable that we had before, that will get us closer. So we were at 300 before, that gets us to 170, and clears up most of the register misuse. So that is a relatively simple change. Is it something that we would have, or I would have thought of on my own to try? Probably not. There's another one where it gets down to 190. The permeter doesn't always know okay, and so this is pulling this line out into a variable, which we're doing before. So let's just try pulling out this first part and then doing the subtraction down here. Let's go back and see what this did. So we have on line 16 here, we have a handful of different registers. And when it's not obvious to me what's happening. It looks like register changes that are slightly closer. So that's fine. It gets us a little closer. I don't know that that's ultimately going to be what helps or hurts, but we'll go with it for now. So then there's a bunch of smaller ones as well that aren't better than the best, but are slightly better. So I usually like to look at those all at once and see if there's anything of interest. So we have the two that we just looked at. Oh, sorry. Starting at the beginning. This is the one that gave us a pretty significant bump, fixing most of the registers. This is the one we just applied, pulling out the call to rand into a separate variable. Let's put the -8 up there just for kicks and see if that. No, that made it worse. Okay, so then this. It's a new variable. That is likely superfluous. I'm not interested in that. No, I don't think those will do anything. one is pulling the argument into a variable before passing it to allocate primitives. I don't think there's much value in that. Pulling out the 8 into a variable. I don't think there's much value in that. Yes, this is actually an interesting one, and I thought about doing this, but then it slipped my mind. So when we have cases like this where we're assigning colors repeatedly, a lot of times these are written as consecutive statements like this. In this case, I don't think it helps us. No, it doesn't help us. And it would actually need to be out of order. If they're in order, that's probably the way that it was written. If they're out of order, they probably were inlined. Okay, we're going to save. Go back and look at what we have. So we're getting a bunch of false positives. So I don't think there's much value to continue on like this. We have gotten it down to 170. So we'll take this version that was pasted in that the permuter was looking at, get rid of that, and put our new version in with the changes that the permuter found, and then start the permuter again. Sorry, I had this in the background. I will not spoil the surprise. So I pasted in our new version based on the few things that the permuter found, and I will run the permuter again. And here we found a score where there's only 60 difference. So let's look at that score. This would be a very, very sad. This I don't think is very likely, but we'll do it for kicks. So it's saying to make a new variable. Before setting the velocity, set our new variable. Okay, and that does lend some value into this happening at a different time, but not like that. I dislike that change immensely, but it got us really close. I don't think that's going to stick. For kicks, let's pull this up into here. That's no closer. I wonder if we pull that whole thing up here. Okay. I'm going to try pulling this to a separate line. Yeah, you get down these rabbit holes of odd changes. So that gets us really close. really don't like that change. Let's see if we got anything better. We do have some that are slightly better. Let's see if any of those look like better changes. Yeah, to me that looks like noise. Most of it is noise. This is the one with the, oh, sorry. This is the one with the 8. Okay, so this is somewhat interesting. And it gives me an idea. So instead of operating on 32-bit for this velocity, what if we change this to a 16-bit? No. And an unsigned 16? No. Now let's try that and get rid of this 8 here. No, we can keep it 16-bit though, because that's more likely. So I'm going through and looking at the other permuter changes. I don't think there's value here either, but we can, so it's doing this. Beforehand. So this change was just to move this out. I guess we'd have to use this. So that is further, and sometimes this happens. You move back a little bit because it seems more correct. The likelihood that there is a variable specifically to hold the 8 is unlikely. This gives us the right structure. We just have the wrong registers. And I'm okay with that. That's why I didn't understand why eventually taking this here and then doing this down here didn't make a difference. Yeah, that's odd to me that compiles differently. I'm happy with this though. So let's take this version and start permuting it. So we're going to let the permuter run. Okay, so the permuter thinks we should make this a regular int instead. I'll buy that. Go to our change, restart the permuter. Registers are probably the trickiest part of this whole process because you can't control them directly. We have a small hint here, though. So going back to what we have in our assembly, if we look at line 13, we're storing this value at an offset in v0, which is our self object. When we do this assignment, the division is happening with a stack register. The V0 and S0 are being inverted. Which reads to me like this, except what is at the first position of our entity is the position x. So and at position is our hitbox offset. So what if this isn't this, but it's this? No. No, it's this immediate value. Ugh. So much of this division doesn't need to take place if we're I'm going to add another variable, and we're going to say this is the, we'll just call it delta, and we're going to set delta to 10, rand, delta. Oh my goodness. And down here. Okay. Once again, wrong window up. We're going to keep this going. The permitter's not going to find this, so we don't have to worry about that. So nobody's tuned in, but if you were, this is one of those things where you get some inspiration and then it works out and you're happy. So we're going to create a new variable. I called it delta. Really, it's kind of the range of how we're going to mess with this. So when I was looking at this rand, and again, I said at the beginning, understanding the assembly isn't important, but in this case, knowing how the assembly works. So we're looking at different operations, or order of operations. The divide that we're doing is really a modulo design. So if taking the modulus is basically saying, give me the remainder of a division. And our remainder, we were saying, give me the remainder of 16 divided by a random number. But the original assembly says, give me the modulo of a random number divided by 16. And that makes more sense. That gives us a value that's between 0 and 15. Usually that's what you want. A lot of times what you'll see in here is they want plus or minus some range. In this case, plus or minus 8. I guess positive 7 to negative 8. So if we take this hard-coded number and move it over like this, the compiler knows we're always dividing by a constant. We can simplify this. There'll never be a divide by 0 because it's a constant. We need to fool the compiler into thinking that there will be a divide by 0. And we do that by introducing a variable that could potentially be set to 0, but never will be. So we're going to set that to our number, and then we're going to do the modulo of that. And one thing I'm interested in, do we even need to do that down here, or can we do it up here? So a modern compiler would look at this, and even though delta is a variable and can be changed, between line 16 and line 17, that value is never changed. So the compiler will just take this 10 and substitute it there. Likewise, down here, we're going to use that same delta variable, but take it on this side, and that was it. So going back to the permuter's gone through 50,000 iterations of possible things that could be changed. It has a set of a few dozen rules that it'll apply to the code to try to match. But sometimes you have to use intuition to figure out. So now I'm interested in, can we get rid of this other velocity variable and do all of this inline? Hopefully that is the case. Nope. We run into the same issue as before. Let's do one additional thing. Let's see if we can at least do these together on the same line. Yes, we can do that. So one thing that might be possible is, if I treat this expression as a 32-bit, does that make any difference? Yes. No, still doesn't work. Okay, that's fine. I don't like it. That's not how I would have written the code, but that is how somebody at Konami chose to write it, or my interpretation of how they wrote it based on decompiling. So we were able to get a match. So our match is at 99%. We have 10 bytes that aren't matching. And if we go through the diff between our target and current, the 10 bytes are in this immediate value, which I mentioned at the beginning, is something that when the assembly is extracted, it doesn't know the offset of this struct, which will compile to the same thing. So I'm going to take this, the function that is matching, I'm going to, in decomp.me, I'm going to mark it as a match, which gives us a nice little endorphin hit with our ribbon. Go back over to our code, replace the one that wasn't quite a match with our new version. And now when we compile, all these objects match. So this code, we started with an assembly representation of code that was taken from an object in the Castlevania, a file in the Castlevania disk, extracted using splat64, which is originally written for N64 decompilation. We took this assembly file, put it into decomp.me to get an initial decompilation. I can speak, really. And then that best effort machine decompilation into a final function that matches. Some of this was done just knowing details about how this code works. Some of it is trial and error, a lot of trial and error. But we got it done. And another function here is now completed. There's a few things that need to be done before this is ready to send in a pull request for cleanup. And this is mostly project conventions and code quality things, but I think this is good to talk about as well, because decompiling is fun and glamorous, but the bookkeeping is important when you're working on a project with other people, and they have to put up with the crap that you you produce as well. So let me top off my soda. So the first thing we're going to do is find these flags that we have macro definitions for. And most of these are going to be unknown, so we don't know what they do. We just know that they're used throughout the code base. So this is going to be a combination of this unknown flag and this unknown flag. And as I'm doing this, I'm semi-dyslexic with numbers, so is that the right number of zeros? I could stare at it for a long time and not know. So I usually just let the compiler check for me, and that looks like it's correct. The second thing is that velocity is a fixed value, not a huge, this would be a massive number. Let's see, it would be a velocity of 49,000 pixels, which you only have 235 to work with horizontally. I guess vertically about 180 or so. So that's wrong. So we're going to turn that into a fixed number. I have a little utility that I use off screen to calculate that value, again because sometimes I have trouble with numbers, and we can use the fixed representation. Other people can read that now and say, oh yeah, I know what that means. So our velocity isn't 49,000 pixels vertically, it's 0.75 pixels vertically. That's a much more reasonable value. And compile again, make sure everything's fine. I think that there's a draw mode in here. Draw mode we have flags for as well. I've not looked into the draw mode code at all, so I don't know what a T page is. Texture page, I'm guessing. So if you remember at the beginning, this was a function for the shield rod. I'm not sure what the shield rod produces. That would require some transparency. A lot of these, it's good to kind of go back and play the game. I often don't go back and play it after I make these changes, but make sure that that works. Great. So, anything else? Any other bookkeeping? just reviewing the code line by line, checking if there's anything obvious that reviewers will note. I don't see anything. It's possible that the T page or color lookup table are defined. Let's see if there's any. Let's see the definition for that. We can wrap it in OVL. Yeah, okay. So this is just saying offset it by the overlay for this particular module or library. And then the other one is T page, texture page, and I don't see anything that's being done with it. So that all looks good. So now we're going to create a commit. This code is shared on GitHub. So we're decompiling and actually I might be in the wrong branch. We're going to create a new branch. We'll call this 007. Pull that into our current branch. We just have that function in there. Make sure that we don't have any conflicts. We don't. So now we're going to push that into GitHub. And we'll go and do the rest over there. So I like to do another review. There's really not anything to say. It's just decompiling a weapon function. I like to make sure that my diff looks like what I was doing in decomp.me. It seems fine. I'll make sure that it builds again. And then I would switch branches. And it doesn't. So why wouldn't we build? I was working in a branch where I had decompiled another function earlier today, and what had happened was there was some assembly code that didn't need to be generated that ended up being generated. That I think was conflicting with that. Oh no, we're still failing. Drat. I don't think there's anything else that back to that other branch. Looks like something else along the way got screwed up, so okay, so let's go back to our function before we change some of those flags. So wait, check and check and check. Because you don't want to send out a PR that you think works fine and then ends up not working. As it was. Oh, this was it. Yeah. So it wasn't the palette overlay. My mistake. So this we can actually go back and undo all that. Go back here. I like base 10. Good. So I only like good commits in my history, so I'll destroy my bad commit and force push over. Okay, back to GitHub. Refresh this. Okay, my initial review seems reasonable. Lookup table. I'm going to check one more thing. Maybe I don't need the palette. Alrighty. Check the delta one more time. Oh, that looks fine. This was the line. Let's see. This is the line that was being changed. So I had wrapped it in a macro that's used to just help differentiate palette palettes that are in an overlay versus palettes that are in the main program, but that doesn't apply to color lookup tables. The rest of this seems fine. One thing I want to do, I'll save this before we continue. I didn't check first to see if anybody else had been working on this function. So decomp.me does let you search for other people who are working on things, and it actually looks like somebody else has started on this 11 hours ago. relatively short period of time. That is quite the coincidence. So they had gotten to 97, and looking at where they were stuck at, they had actually figured out pulling out the modulus into a separate variable. This ended up looking very close to what we produced. Not exactly, but relatively close. So a few differences, which are all reasonable. Instead of returning from this main if statement, they use an else. No issues there. My own personal style typically is to keep code as close to the left side as possible. So if I don't have to nest something in brackets, I try to avoid it. And so that means I like multiple returns because I'd rather terminate a block than have that continue on. So what ended up being their issue? And I think I see it, but it's unfortunate and would be relatively hard to have found. Actually, may or may not know who this particular developer is. But let's see if my theory is correct. So what we did in ours was take another variable and then assign that here. No. But we also add this down here. Still doesn't fix it though. Let's look at ours. Lovely. I want to open the image init tab. This looks an awful lot like mine. But they're still having register issues. Let's see if I can get these as close as possible. So I can flip back and forth between them. Name differences, and the only difference that I see, and this is going to be stupid if it's the case, no? Huh. Oh, what happens if I, yeah, that works. Well, I'm not sure what the difference here is. I mean, they have a lot of the macros in that I ended up putting in separately. Oh, I see what the difference is. It has nothing to do with line 21 at all. It is down here. And this is actually found by the computer and not by me. And now it works. Okay, well that's interesting. Sometimes looking at somebody else's though, it's not obvious what the issue is. So normally now I would go through and I would submit this, and I guess I will. Why not? Spell decompiles. So I'll create the pull request. When the pull request is created, a bunch of checks will happen. It'll build the PlayStation version, the PSP version, a PC version, and make sure that the code that's being submitted builds all those places. I happen to know that the weapons themselves aren't built anywhere but the PlayStation version, so I don't check anything but the PlayStation version if I'm not changing anything that isn't going to affect those other places. So yesterday we submitted a PR for Weapon 15, and that one was approved, and it was merged in shortly after. So the Castlevania Symphony of the Night decompilation project is extremely active at the moment. There is about a half dozen regular contributors submitting PRs, trying to figure out what the structure of that game is, how sounds are produced, how assets are stored, what the best way for us to take those original objects from the game, extract them, be able to manipulate them, or make changes, produce ROM hacks and things like that, and then pull everything back together. By default, making exactly the same objects that were shipped in each of the different versions of the game. If decompilation is something that's interesting to you, definitely take a look at decomp.me. There are lots of projects that are actively being decompiled. One of the ones that I came across recently was it Loaded for the PlayStation? I've come across a few different PlayStation games along the way that I'm not contributing to at the moment, but would be interested in contributing to in the future. Castlevania Symphony of the Night is one of my favorite games on the platform, a game that I found nearly 20 years after it was made, but adore it to pieces, and I'm really excited that I get to be helping in as little way as I can to decompile it so that people in the future can make mods, make tweaks, fix bugs, and hopefully preserve this game for the future. Anyway, thanks to anybody who tuned in. I'm going to be trying to do this for about an hour a day during the weekdays. If you're interested, please subscribe, follow, chat, and I will see you all on Monday.